Alright, time for another draftphysics.com, debatephysics.com video presentation. Alright, so the Blue Moonshine guy, we'll just call him that, has made a response video where he's not doxing or doing anything obnoxious, so I can probably play his video, hopefully. And he's claiming he's proving, okay, the work energy theorem. And there's absolutely no proof here at all. He's not going to prove that twice the velocity is 4 times the energy. He's not going to prove that 3 times the velocity is 9 times the energy. He's not going to prove that 4 times the velocity is 16 times the energy. So it's not even going to come close to giving any demonstration of what he's claiming at all. And I really shouldn't have to explain that to a physicist, frankly, that this isn't evidence of the theorem. Okay, that velocity produces squared amounts of energy, that it does squared amounts of work. So obviously Galileo, Newton, and Descartes all knew this, okay, basic function, okay, that things go faster as they fall. And Galileo, quantified it quite well, okay, that in the first unit of time, that's 1 unit of time. All right, you go this little tiny bit of distance, okay, but you're actually be going half your velocity right there, okay. And this rest, okay, because you're gaining velocity, right here you get that, if it was 1 second, you'd have 9.8 meters per second of velocity now. And so these next 2 units of distance you would get for free, all right. You don't need any gravity for this to happen. You're going to get this motion if gravity's turned off entirely, and all you're going to get in the next, let me just make this line longer so they're a little bit equal, this is all you're getting, this part, okay. This is the 4.9 meters, okay, if we're talking about a 10-meter fall, that you're going to get as new motion, actual motion, and you're going to get another 9.8. So you got 9.8 here, you're going to get 9.8 here. You're only going to be going, okay, 19.6 when you hit the ground. It's only twice the velocity. You're only in the force 2 units of time, so it's just 2 units of time, all right, 2 units of velocity. There's no evidence that there's 4 units of anything. You didn't get 4 units of gravity. You only got 2 units of gravity because it's 9.8 meters per 1 second. And so this doesn't prove, because you go 4 times the distance, you're not proving it did 4 times the work or had 4 times the work done on it. It only got 2 units of velocity. It was only in the gravity 2 units of time. It doesn't prove anything at all. It certainly doesn't prove 3 times the velocity is 9 times the energy. It's not a proof. It's not evidence. It's not even close to meeting the burden. So it's just a sham that they would argue that who are you fooling? Okay, anybody who really knows anything about what the argument actually is, the argument is about the squared velocity meaning an increase in energy. It's the 1/2 mv squared part you're supposed to be proving, and you're not proving it by dropping something in gravity. Because if Galileo didn't believe in 1/2 mv squared, Newton didn't believe in 1/2 mv squared, and Descartes didn't believe in 1/2 mv squared. They all knew that things fall faster as the longer they fall in gravity. So they all knew, okay, that it's a time-dependent force. And so quit pretending that they actually thought twice the velocity was 4 times the energy, because right under the second law, Newton clearly stated twice the force, twice the motion, 3 times the force, 3 times the motion. So this is just such a distortion of the truth. It's such a lie, frankly. Just lying. Alright, so let's play it.
In this video, we are going to experimentally test the validity of the work energy theorem.
So all this does is slow it down, right? This is just like dropping the object. All you're doing is putting it on a ramp, so you're going to make sure that the motion is slowed down. So you're just going to have exactly the same motion. You're just slowing down the process. So you're going to be in gravity much longer than if you just drop the object from a height. And it's going to create more friction and different air resistance, whatever ever. And the fact is, yeah, but you're going to get the same result. You can't change the fact that in the first part of the motion it's going to be moving very slowly, and it's not going to go very far. And then this next part of the motion is going to be much larger because it already has a velocity. And so this doesn't prove anything. Everybody knows 4 times the distance is twice the velocity. It's not 4 times the velocity. You have to explain how twice the velocity is 4 times the work. And there's no evidence of that ever, anywhere. The Mythbusters crash the cars, okay? Twice the crushing at twice the speed. Not 4 times. It's just so wrong and deceptive to argue that this proves anything at all. This is a nice way to slow gravity down. And that's all it is. It doesn't prove how much energy the object has.
And check whether the quantity that we defined as kinetic energy is meaningful or not.
Yeah, so he's not going to measure anything called energy. He's just going to claim it has the energy because the V is squared. You haven't proven that.
Experimental setup consists of a glider moving on an inclined air.
So I made all those little arguments. Maybe I'll interject in this video somewhere. I'll go back and listen to all my ways of testing your air track setup. You know, by having it bounce back and forth, all right, and see if it goes any faster when it hits a spring. See if the cart tips at all. Because again, he has his carts way weighted, okay? He has the impact point way above the center of mass, way above. So the carts are obviously going to tip.
Track with negligible friction, a motion detector that can record the position of the glider as a function of time, and a computer that allows us to analyze the collected data.
This is nothing. I mean, this is just like dropping it, have a stroboscope, take pictures at an set interval of time, and you'll see exactly the same thing. This proves nothing. This is going to be a long waste of time. Me just saying you haven't proven anything. You haven't proven anything. We all know this already. We already know this. Galileo already did this. Yeah, the air track's better because there's less friction, but it's still the same experiment. It doesn't change anything. It'll just go a little bit faster.
Let us start by analyzing the problem with a free body diagram of the glider.
I mean, when Galileo was rolling a ball, the fact is he was creating more than just linear motion. The linear motion of the ball was one thing, but it was all rotational energy was also in the ball. So, you know, that's why it had to be even slower. So that's why it was a nice experiment, because everything happened so slowly. It's not going to happen as slow this way. You know, this way you're not going to slow it down as much. So it's almost like you might as well just drop the damn stuff.
As for any problem that involves an incline, it is a good idea to choose our x-axis parallel to the incline.
So you could have just the tiniest bit of a height increase, and then it'll be as slow as possible. You can make it go really slow by just making that incline tiny.
Positive direction is chosen to point away from the detector. The y-axis is, of course, perpendicular to the x.
I mean, this is the second time he's made a video doing this kind of rickety crap, like is just moving a cart of velocity and then measuring its acceleration and then claiming that somehow proves it has 9 times the energy or 16 times the energy or 25 times the energy, and it doesn't prove any of that. The velocities aren't in dispute. Nobody's disputing the actual velocities. What they're disputing is your notion that somehow it has quadratically increasing amounts of energy. That's what's in dispute.
Axis pointing up. We call theta the angle that the incline makes with the horizontal. Since friction is negligible, there are only 2 forces acting on the glider. Its weight, vertical downward, and the normal force exerted by the...
So there's no normal force. That's all crap. So, you know, obviously there's no friction, there's no normal force, there's just air it's floating on. And yes, it floats at a position, which ends up being the same thing as just sitting in gravity. But again, you don't need to understand any kind of normal force, because there isn't in a normal direction. The fact is, because of the tiny tilt, you have a tiny amount of height, of, you know, gravitational height. And so, you know, it's just going to really slow down the process of that force going down being converted into a linear force. You're changing almost all of the energy from force going this way to force going that way.
Air cushion perpendicular to the air track and upward. From basic geometric considerations, it follows that the angle between the weight vector and the y-axis is the same as the angle between the track and the x-axis. The glider obviously cannot sink through the air track, neither can it take off on its own. Thus, there is no acceleration along the y direction. It should be clear that the acceleration will...
Well, whatever. Obviously, when you have it tilted, there is acceleration in the y direction, but whatever, who cares?
Will be
I mean, this is just a waste of time.
Parallel to the x-axis in the negative direction. Using this angle, we can replace the weight vector by its x and y components. From trigonometry, we find that the x component of the weight is negative mg sine theta, and the y component is negative mg cosine theta. We can now apply Newton's second law. In the x direction, the only force is the x component of the weight, which is therefore equal to the glider's mass times the acceleration, so that the acceleration is equal to negative g sine theta. Since there is no acceleration along the y direction, the normal force must cancel the y component of the weight, so we find that the normal force is equal to mg cosine theta. The important result here is the acceleration, from which we conclude that the net force is equal.
Like I said, Galileo did this, right? So he told us, he gave us the odd number theory, right? 1, 3, 5, 7, 9. I mean, come on. This is not arguable.
To negative mg sine theta. Since the mass m, the acceleration due to gravity g, and the angle theta are constant, we conclude that the net force itself is constant. In particular, it doesn't depend on the position of the glider along the track, neither does it depend on its velocity. Let us...
It certainly depends on the angle, the height of the glider. So yes, obviously if I make the angle this, it just free falls and drops at free fall rate. If I'm changing the angle, I'm causing it to push down more, okay, and have to convert the motion this way into motion that way. And it's that conversion that's going to slow everything down.
Calculate now the work done by the net force. For this, we start from the general definition of the work done by a force as the integral of the force from some initial point I to some final point F. Now, if the force is in the direct...
The simple fact is if the air track were being weighed, okay, you were weighing it, and you did this experiment, and so the cart started where it's not being weighed, in air, and then it falls off the end of the track, you could understand that the cart will now be on top of the air track for a longer period of time, which means the whole device is going to weigh more because it's collecting more force of gravity because it's in the gravity longer. So it is doing more work on the ground. It's actually causing some motion into the earth because of its weight, because of the time it's sitting there. Right now you're putting weight into the earth at a constant rate. The same thing's happening here. So it's not the same energy as free fall because a bunch of energy is being absorbed into the earth through the whole experiment. The weight of the cart is pushing down on the earth
of the displacement and is constant, which is the case for our net force, then the work done is just equal to the product of the force and the displacement. Substituting our previous expression for the net force,
the air pressure is pushing down on the cart. It will actually weigh something. The whole track will weigh more because the cart is pushing down on the air, creating air pressure.
We find that the corresponding work is equal to mg sine theta times the initial position xi minus the final position xf. The reason why the initial and final positions have been exchanged in this last expression is because we have a negative sign in this expression of the net force. Alright, so we have an expression for the work done by the net force, but now let's calculate it in another way. We start again from the general definition of work, which we apply to the net force, but this time we substitute Newton's...
Right, so you're just telling us that this is your definition of work, that this is somehow a real formula that really gets real answers, and it doesn't. You haven't proven twice the velocity is 4 times the work. You haven't proven that v squared makes any sense at all.
Second's law for the net force. We find that this work is the integral of the dot product of ma with the infinitesimal displacement dr. Since the mass is constant, it can be moved out of the integral. Also, we can use the fact that the acceleration is the time derivative of the velocity, and the infinitesimal displacement dr is the velocity times the infinitesimal time dt. Next, we can use the fact that the dot product of the time derivative of the velocity with the velocity is equal to 1/2 of the time derivative of the speed squared. And finally, we can use the fundamental theorem of
Just bang the cart into a clump of clay and see if you can get it to show 4 times the crushing of the clay. Find something to measure the impact force. The impact force. The impulse force of the cart going twice the velocity, and show that twice the velocity is 4 times the impact energy. That's what you need to show.
calculus to replace the integral of the derivative of a function by the change of the function. So we end up finding that the work done by the net force is equal to 1/2 of mvf squared minus 1/2 of mvi squared. As a result, if we define the kinetic energy to be 1/2 of mv squared, then we have proven the work energy principle, which states that the work done by the net force is equal to the change in kinetic energy. So let us apply the principle to a particular case. We found earlier that the work done by the net force was given by mg sine theta times initial position minus final position, and the principle says this must be equal to the change in kinetic energy. This allows us...
The principle, that's not right. Okay, so you just keep telling us there's a v squared, and it does something, that it's real. And I keep making arguments over and over and over again, dozens of them now, pointing out how it fails the ballistic pendulum test, it fails the lever test, it fails pulleys, it fails hydraulics, it fails every test you put it to. It doesn't work. And you keep claiming it does work. It does do work. And in every case, it doesn't do any work.
To predict the value of the final velocity if we know the initial velocity and the change in position. So we are going to experimentally test this prediction.
So this isn't a prediction. You're not going to test the prediction. You're just going to test that it's twice the velocity. Yeah, we all know it's twice the velocity. You know, you haven't 4 times the distance is twice the velocity. We all know that.
Here is the air track, which is currently level, and here is the motion detector and the computer that will record the data. Let me put the glider on it and see how it moves almost frictionless. Its velocity is nearly constant according to Newton's first law. Let us measure its mass.
I don't know how its velocity would be nearly constant if it's tipped, so I guess it's not tipped yet.
Although we won't need it since we saw that the acceleration and the final velocity do not depend on it. 391.9 grams.
So instead of doing the experiments I suggested, you know, he's doing this, which is no better than just dropping something, you know, and photographing it in slow motion and demonstrating that it goes half its velocity when it traveled 1/4 of the distance, and then it goes the other half of its velocity traveling to 3/4 of the distance. And it only gets 2 units of velocity, and it only takes 2 units of time to drop 4 units of distance. So again, just ignore all the real facts and just do this nonsense.
Let me put the camera on the stand. Alright. We should check that the track is level.
So it's level, then what are you doing? What's the point of this experiment? I don't know.
It should be, since I didn't touch it since my last experiment.
So all he has to do is put a spring at the end here, push his cart against the spring, and see if the spring, when the cart leaves, if it's leaving at a higher velocity, you know there's something wrong with your air track, the way you've laid it out. The way you have your objects hitting each other way above the center of mass isn't a good idea.
Yes, it does not accelerate, so the track is level. But now, I'm going to insert a spacer under one of the feet. This results in some angle that we are going to estimate, and this angle is enough to give the glider a substantial acceleration.
Yes, I really thought you'd get around it. I mean, what's the point of testing the level when you're going to raise it anyway? But whatever. So it's exactly like free fall. It's just much slower.
Alright, to determine the angle, let us check first the distance between the feet. There is a foot that is on the 50 centimeter mark, and the other is on the 150 centimeter mark. So the distance between the feet is 1 meter. Now let us measure the size of the spacer, and for this I'm going to use a precision caliper. Let's see, I'm trying not to knock off the camera.
So all of this is just so wasted time. There's nothing here that's under controversy. None of this is anything that's ever been argued about the outcome of this experiment. 400-year-old experiment. that Galileo and Newton clearly were both aware of. Neither one of them said, oh, that means there's 4 times the energy. Twice the velocity is 4 times the energy. No, neither one of them said that.
Let me try to focus. There is 15.43 millimeters. So let's pause here and determine the angle of the incline. We know that the distance between the
So he's raised it 1.5 centimeters.
track's feet is 1 meter or 1,000 millimeters, and
So the object's only going to fall 1.5 centimeters. So when it hits the other side, I could argue that it's going to weigh 2.25 times its gravitational weight. But that's going to be the impact weight. I wonder if he'll test for that. That's my prediction.
the spacer we added is
1 centimeter is equal to your 1 centimeter of motion, momentum, is equal to your gravitational weight. So if I move you at 1 centimeter per second, it'll be the same thing as 1 mile an hour. 1 centimeter, not 1 centimeter per second. If I lift you in 1 centimeter in gravity, you'll be going 0.44 meters per second. And 0.44 meters per second is 1 mile an hour.
15.43 millimeters. So we can calculate the angle to be 0.8840 degrees. Also, this leads to an acceleration of negative 0.1512 meters per second squared.
Yeah, how much do you predict that the object will weigh when it hits the wall? How much momentum will it demonstrate itself to have? And the fact is, your prediction will be the same as mine, because the kinetic energy is just a made-up number. You're claiming it exists, but you're not going to prove it exists.
Alright, so let us do the actual experiment, and it is going to be extremely fast. All we have to do is to set up the computer to record the motion, and give the glider some initial push away from the detector.
So you could just let it go at the other end, right? Same difference. So, doesn't change much of the experiment to throw it and then have it come back again, because we know it did exactly the opposite. It slowed down exactly the way it's going to speed up.
Done.
That should be visually
Now let us analyze the collected data.
apparent.
The top graph shows the position versus time, and the lower graph is the velocity versus time.
So instead of showing us the forward, so this is the curved line of the changing acceleration. So it doesn't really show it very well, exactly the fact that it has a, that arc is getting flatter at the top, and then it gets, greater as it goes down.
Let us change the scale of the velocity graph. Alright, the velocity is noisier than the position, which is normal since the detector actually measures only the position, and the velocity is determined by performing a numerical derivative of the position, which is an operation that always amplifies the noise. But still, the data are good enough for our purposes. The first
Oh no, it'd be a lot nicer to see the velocity.
thing we can do is a linear fit of the velocity in order to obtain the slope, which is the experimental value of the acceleration.
So this is apparently 0. I don't know. It's not, this chart is a little bit vague.
Negative 0.1466 meters per second squared. Remember, our prediction was negative 0.1512 meters per second squared, so we have a percent difference of 3.1%, which isn't bad. The experimental value has a magnitude that is smaller, and this is not surprising since we neglected the air drag.
Yeah, so this means nothing. Again, this is, like I said, Galileo dropped things straight up and down and said, oh, that happens way too fast. So let me put it on a curve, and then it'll slow everything down, but it'll do exactly the same thing. It'll fall at exactly the same proportional rate. You won't change anything about the experiment except you'll slow it down. And that's all he's demonstrating here. That in the first unit of time, you get half your velocity. And then the second unit of time, you go 3 times the distance, and you only get 1 unit of force. And you only end up with 2 units of velocity, and you're only in the gravity 2 units of time. and you really only have 2 units of weight.
Alright, so let us choose a random initial point, for example the one at time 0.20 seconds. So we take the initial position to be 0.597 meters, and the corresponding initial speed is 0.331 meters per second. So if we take the
1, 3, 5, 7, 9, again, it's going to do exactly the same ratios. If I make it a half second, I make it a quarter second, it doesn't matter. It's all going to be the same exact ratios. 1, 3, 5, 7, 9. It's going to do the same damn thing.
Final position to be 0.792 meters, we find that the corresponding final speed is 0.226 meters per second, while our formula predicts a final speed of 0.225 meters per second. Thus, the percent difference is only 0.44%, which is excellent. Let it
0.44, yeah. So yeah, you can just turn this to number meters per second into a momentum, and then you can just turn that into a weight.
Let's take another final position of,
I mean, you move it at 0.44 meters per second, so whatever his numbers were. I guess I go back a little bit. You know, that's 1 mile an hour, so it says here 0.22, so it's half that speed. It's a 1 centimeter drop, 1.5 centimeter drop. So frankly, it should be, yes, twice the speed, right? Yeah. Well, no, 0.225 is slower than 0.44. So there's something wrong in there somewhere. 1 centimeter is 0.44. A centimeter and a half has to be something like, 0.66 or something.
which is excellent. Let us take another final position of 0.878 meters. The experimental final speed.
Just trying to think of what the catch would be. Is that it's not really a full centimeter and a half because he didn't go across the whole track. So he's stopping it before it fell all the way to what would be called the 0 point. So because he didn't go to the end of the track, he didn't go to the 0. So he cut it off with less than a centimeter of drop. That's what happened.
It is 0.158 meters per second, and our formula predicts a speed of 0.157 meters per second. The percent difference is 0.64%, which again is really good. Now let us take another final point close to the point where the glider changes direction. For example, 0.958 meters. The experimental speed is 0.024 meters per second in the negative direction, and for this point we can't expect the prediction to be as good because since the speed is almost zero close to that point, we have a loss in numerical precision. Our formula predicts a value of 0.20 meters per second, so the percent difference goes up to 18%.
That's a pretty huge difference, yes. So what's his excuse? I don't remember, but anyway, it doesn't matter.
But we recover an excellent agreement when we move away from that point. For example, at 0.486 meters, for which the experimental speed is 0.378 meters per second in the negative direction. This is the exact same value as the prediction, so we have a perfect agreement.
Why don't you take the velocity at the final point, the last velocity reading? That would be the most relevant one. But regardless, it just doesn't matter.
And here. To conclude, this experiment supports the validity of the work energy principle.
So it doesn't support anything. It doesn't in any way show you that it takes 9 times the energy to move something 3 times as fast, and it certainly doesn't show you something going 3 times as fast doing 9 times the work. So it has absolutely nothing to do with the subject, doesn't provide any evidence whatsoever. And again, Newton knew about this. If Newton already knew about this 1, 3, 5, 7, 9 thing, then why the hell, okay, if he thought, why would he say twice the velocity, twice the force, 3 times the velocity, 3 times the force? Why would he say that if he thought there was a squared velocity function? So again, you haven't done anything but, try to dupe the ignorant. That's all. You're just trying to dupe the ignorant.
As well as the meaningfulness of the concept of kinetic energy.
Terrible nonsense. What a bogus, fake, phony video. Ugh, people suck.
The world's first titanium nonstick.
That's just the truth. Humans are appropriately considered garbage. So let me just draw it one more time. I mean, all dropping the ramp is like putting a ramp in a stream. right? So you put an object in the stream, it just goes in the stream. But if I put a ramp on the surface of the stream so the object can't go with the stream, it has to move across the ramp that I put in its way. And the more perpendicular to the flow of the stream I make that ramp, the slower it will move. But it will move at exactly the same acceleration rate that it would have this way in terms of proportions. And so, again, we'll just draw it. 1 unit of distance, half your velocity. The other 3 units of distance, okay? And you only get the other half of your velocity. So you only get 2 units of velocity, 4 times the distance. You're only in it 1 unit of time here, 1 unit of time here. So it's only 2 units of time. So it's only 2 units of velocity, 2 units of time. It will be 2 units of weight, plus your gravitational weight if you do it in this direction. And all the ramp does is exactly the same experiment, and it has exactly the same results. Your starting velocity is very slow, and then you get your next 3 units. Okay, you're only getting 1 unit of extra force. That's it. This is all you're getting, because it's 2 units of total time. This will be a unit of time. Whoops, this will be a unit of time. All right, time, and this will be a unit of time. So you get the same proportion, same outcome. You've just slowed down the experiment. And nowhere in any of that nonsense are you proving that something going twice as fast was in the gravity 4 times as long, because it wasn't. It was only in 2 units of time. You're saying 2 units of gravity is 4 units of energy. Obviously, I'm saying that's absolute nonsense. And as I pointed out, you can logically understand if I did actually drop something this first unit of distance, and then I turn the gravity off completely, it's still going 9.8. So it's going to get these 2 units for free. These are free. There's no force required, no added force required to get these 2 units. And it'll keep going 9.8, 9.8, 9.8. It'll keep going those 2 4.9 units of distance forever, theoretically, without any more force applied. And so this is the only unit of new force. This is the new force. This is the new force. That's all you got. 2 units of gravity, 2 units of force, 2 units of time. You can't have 4 units of energy because you only got 2 units of the thing that makes the energy, the force. All right. So again, evade all my arguments and do an experiment that proves absolutely nothing regarding the theory that somehow energy quadratically increases with your velocity. Something Newton didn't believe.